So I'm going to make two videos for today because we're going to talk about two topics when we're introducing logarithms. The first video will cover logarithmic graphing and compared to graphing the exponential function. So just a quick reminder, we learned about the basic log function and basic exponential function when we did the basic functions at the beginning of the year. Our basic exponential function was y equals 2 raised to the x power. And some properties of that exponential function, it has a horizontal asymptote that is the x-axis, so y equals 0 is a horizontal asymptote. And if you go to the table, it has a y-intercept right here at 0, 1. So if we go back to the equation y equals 2 to the x, so if we, 2 to the 0 power, anything to the 0 power is 1, y-intercept. 2 to the first power would give you the 0.1, 2. 2 squared would give you 2, 4. So those are points on the graph. But no matter what exponent you put in for x, you will never have a y value that is negative or 0. So it doesn't matter how small the next value, it's never going to be negative. Like these numbers are just super, super tiny, but they're never going to be 0 and they're never going to be negative. And then the inverse of the exponential function is the logarithmic function. And so it would also have a base of 2. So I did alpha window, and number 5 is log base. So log base 2 of x is the inverse of the exponential function that has a base of 2. So that function instead has a vertical asymptote. I can't draw that as easily, but the y-axis is a vertical asymptote. And even though on the calculator, it looks like the graph just stops, this graph does continue getting closer and closer to the y-axis and does go down to negative infinity. And so since they're inverse functions, the exponential function had the, let's see, put that back in, 2 raised to the x. So remember, the exponential function had a y-intercept of 0, 1, but your inverse log function has the x-intercept of 1, 0. And then if we think about when we learned about inverse functions, for two functions to be inverses, they have a line of symmetry that is the identity function. And you can see that would be a line of symmetry for those two functions. So again, even though the calculator makes it look like the blue graph just stops short, it does continue just like the exponential graph does. Okay, so let's look at some of the notes. So you have the notes that are provided for you in the module. So some of the stuff that I just talked about, we have your basic exponential function, y equals 2 to the x, and we can create a table by substituting in these different x values. Remember, if you have an exponent that's negative, it doesn't make the answer negative, it makes it move. So 2 to the negative 3 power is just 2 cubed, but you move that 8 to the denominator. And 2 to the negative 2 power is 2 squared, but in the denominator. 2 to the negative first power is 1 over 2. Anything to the 0 power is 1. 2 to the first, 2 squared, 2 cubed. And you can plot out those points and see the same shape that I showed you on the calculator. There is, again, that horizontal asymptote of y equals 0. The domain of all exponential functions is negative infinity to infinity, and the range is going to be based on the asymptote, and because it's an asymptote, you use a parentheses. So since the asymptote is y equals 0, the range is 0 to infinity, but the parentheses is used because the asymptote says that y actually can't be 0. So the inverse is the log function, and if the base of the exponential function is 2, then the base of the log function is 2. So if you take the table of values from up here, for inverses, everything to do with inverses is about switching x and y. Okay, back when we did inverses, I said that over and over. Anything to do with inverses is about switching x and y. So if the domain of our exponential function is negative infinity to infinity, then that would be the range for its inverse function. If the range is 0 to infinity, then it's the domain for the inverse function. And if the asymptote is a horizontal y equals 0, then for our inverse function, it would be a vertical x equals 0. Then we take the same table, and all these x's become the y's, and all these y's become the x's. So here's our table of values, just switching the x column with the y column. And then when you plot these ordered pairs, you can see you get that inverse graph that I showed you on the calculator. So does the domain and range and the asymptote you choose match your graph? Yes. The characteristics of the graphs of the logarithmic function, it's f of x equals log base b of x. The x-intercept is 1, 0. The y-axis, or x equals 0, is a vertical asymptote. If the base is greater than 1, the function is increasing. And if the base is between 0 and 1, then the function will be decreasing, and the graph is a smooth, continuous curve. So then we want to take those basic functions and look at the transformations that we learned back when we talked about the basic functions. So if you add or subtract a value to the end of the equation, that moves it up or down. We're using C here, but if you think A, H, and K, this is the same as K. So at the end of the function, if it says plus something, you go up that many, and if it says minus something, you go down that many. If the thing you're adding or subtracting is trapped with X, this would be like H. C is just being used for constant here. So this is like H. It has to be trapped with X, and it's opposite of the sign. So if you see X plus something, it goes left, and X minus something, it goes right. And then we have the negative, that would be your A transformation. That would multiply all your Y's by -1, also reflects it over the x-axis because it's the opposite of y. And if the negative is trapped with x, that's a B transformation. It multiplies all your x's by -1, or you can think about it reflecting over the y-axis. So let's look at some of those graphs. So this is the parent function that we already graphed originally. So it's the same values that I've already graphed. This is the same function, except this would move left 2. So the vertical asymptote shifts left 2, and all other points shift left 2. Basically, to graph a log function, you need to get the asymptote in the right place. You need to get the x-intercept moved to the correct place. So as long as you had the asymptote drawn in at x equals -2 and the x-intercept moved over 2 places to -1, 0, and then you knew the shape of the curve, that would be enough. So this would be the original graph moved down to. That does not affect a vertical asymptote. The only way to move a vertical asymptote is to shift it left or right. And it would, though, move your x-intercept down 2, and then you have your shape of the curve. And then in example 4, this is an A transformation, so it reflects everything over the x-axis because it's the opposite of your y's. And so if you do the opposite of y, you flip it over the x-axis. So it just flips this curve around over the x-axis. So now it is decreasing instead of increasing. The vertical asymptote's in the same place. The x-intercept's in the same place. It's just the direction of the curve. So some general information about graphing logarithms. This is all the transformations that we just looked at. So A is a reflection over the x-axis, B is a reflection over the y-axis, H moves the graph right or left, and K up or down. So these are some basic points that you want to start with. 2 is the base of the log. So if we always do the x-intercept point and then have x equal to its base and x equal to the reciprocal of its base. Those are kind of just going to be a pattern that we're going to follow. And then we can just, the way this is going to work is whatever the base of the log is, your y value is always going to be 1, and 1 over the base is always going to equal -1. That would be true for the log function with a base of 2 versus our exponential function. See how we can flip that? So for the exponential function, you would use the x values of 0, 1, -1, and your y's would be 1, whatever the base is, and 1 over the base. And then that just flips over for your log function. Your y's are 0, 1, -1, and your x values are 1, whatever the base is, and 1 over the base. So these are the graphs that we looked at earlier, these reciprocals, inverses. Okay, so again, here's sort of your template. Whatever the base of the log is, you're going to use as your, for your x values. So this is y equals b to the x. For a log function, you're going to have the base b, or the exponential function has the base b. And so for a log function, you want to use the x values of 1, whatever the base is, and 1 over the base. And your corresponding y values will always be 0, 1, and -1, regardless of what this base is. Then we have something called a natural log. A natural log has a base of e, and we just use the abbreviation ln. E is like pi. So if I say pi, you guys all know 3.14. Well, there is an irrational number that represents e, but we use 2.718. Okay, it's just like pi is a number that showed up in circles long ago. E was a number that showed up as a relationship in exponential and log functions long ago. So if our base is e, whether it's exponential form or in log form, you're still going to do your x's of 1, the base, and 1 over the base. So e is represented by 2.718. That's the rounded number. The real base e is irrational, just like pi is. And then 1 over the base, 1 over 2.718, we round to 0.368. And then the y's are still at 0, 1, and -1. So if we do a base of 3 on our log, then our table would be 1, the base of 3, and then the reciprocal of the base 1 over 3, and our y's are still going to be 0, 1, -1. Okay, so that's going to be constantly how we set this up. So the vertical asymptote would be the y-axis unless there was a shift left or right. So we have a vertical asymptote at x equals 0. And then we can make our short little table based on this template and the base of the log being 3, and we can graph these points. Again, for the most part, you just need the asymptote in the right place and the x-intercept in the right place. The domain is based on the asymptote, so 0 to infinity. The range of all log functions is -infinity to infinity. And this shows growth because as x gets bigger, y is also getting bigger. So if we apply that to a log that has a base of e, and again, you don't write log base e, you write natural log. So you've got your x is 1, the base is e, and then 1 over the base. And those y values are always still going to be 0, 1, and -1. The domain is still going to be based on that vertical asymptote at x equals 0. The range is always -infinity to infinity. So it's still growth. The only difference is really these other 2 points. You still have the x-intercept of 1, 0. It's just the other 2 points are slightly different than we had up there, but the general shape is the same. If I was only graphing the vertical asymptote and the x-intercept, you really wouldn't notice any difference whatsoever. So that is your basic graphing video, and next will be some logarithmic basics.